Hello guys, welcome back to my channel. Take two, take two. It's wrong. Hello channel, welcome back to my guys. We have this one. Frustum of a sphere. In this video, we are going to discuss the different ways of solving for the volume of the frustum of a sphere. Okay, let's proceed. We have this problem. I will load my video for a pretty face. That's what my mother told me. All right. Let me check. I am speaking dollar today because I am targeting my global audience for Mataleno. All right. It's really hard for me to speak to it to discuss in English, straight English, but I need to so that I can communicate with my audience from other country. Most I am actually doing course videos for my course in algebra. My videos there are in Tagalog, so this is my for a long time again. Today I am speaking in English and hopefully I can endure and you can endure to listen to me. Let's proceed. A sphere of diameter 40 cm is cut by two horizontal planes. So we have this sphere. Of course, the radius is 20, laser pointer. The radius is 20 because the diameter is 40 cm. Okay? Then we are going to cut this sphere by two horizontal planes. These are our cutting planes. Okay? One plane is 8 cm below the center of the sphere. We have this radius 20. Below the center of the sphere, we have this cut. Okay? And the other plane, or the other cutting plane, is 14 cm above the center of the sphere. Alright? The required is the volume of this frustum formed by this cutting plane. So we call this type of volume the frustum of a cone, or the longer version of that name is spherical segment of two bases. The question here is how to solve this problem. That is the that is the question. So how can we solve this problem? Excuse me. There are many ways. That is the purpose of this video. I am going to present it. I am going to present, I think, four. If I'm not mistaken, I think four. Okay, four solutions class to solve this volume. Of course, the traditional solution, our traditional approach, we are going to look for a formula that is exactly applicable to this type of volume. That is our usual route in solving problems. Okay? If there is a formula and you memorize that formula, that is very good approach. Okay? So what is the formula for the spherical segment of two bases? If you can memorize that one. If you cannot memorize that spherical segment of two bases, you can actually do the spherical segment of one base. But I did not prepare it for this video for the spherical segment of one base. You can do that this whole sphere minus this spherical segment below of one base minus this spherical segment above. Okay, with one base, what remains is the volume of the sphere, volume of the required volume. Okay, how about this for directly the direct formula for the spherical segment of two bases? The formula is this one. The volume is equal to pi h all over 6. Okay? Times 3a squared plus 3b squared. It's a little long formula. Plus h squared. That is our formula. What is this h actually in our formula? That is the distance between the bases. The upper base and the lower base. Okay? That is the value of h. From our figure, that is equal to 22 cm. Okay? 22 cm. 8 plus 14. How about what are these A and B? What are these values? These are actually the radii of the lower base and the upper base. Doesn't matter which one you call A and which one you call B. Okay? In this solution, I will call the radius of the lower base A. So by Pythagorean theorem, we can solve for the A squared. We don't need actually the A. We only need the A squared. Let's do that. We have this Pythagorean theorem, hypotenuse squared, okay, plus A squared, okay, is equal to plus, what is that? Hypotenuse squared is equal to A squared plus 8 squared. That's why if we are going to solve for the A squared, we will have this hypotenuse squared minus 8 squared, that is from Pythagorean theorem. So we can get this one in our calculator. Boom! 336. How about the upper base radius? This radius here, we call that B. What is the value of B squared? Okay, the B squared is equal to hypotenuse squared by Pythagorean theorem again, minus 14 squared. Okay, that is equal to 204, baby. Okay, substitute to the formula. That is the good thing about traditional solution, traditional approach. If you have the formula, and if you have the elements in the formula, the values of the elements in the formula, you can get the solution of the problem. Pi h all over 6, blah, 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 blah. That is our answer. Chicken joy, baby! 24,236.34 cubic cm. Okay? Actually, no, the disadvantage of this type of solution is the formula itself. If you cannot recall the formula, or if you did not memorize the formula, that's the problem. Or if you don't know that there is a formula that exists for this one, that is the problem for this approach. But if you have this formula, you can do that. Okay. So so far now for this video, we are going to solve this problem in another way. So I have here another type of solution. Solution by Prismatoid. Actually, we're also going to use the definition of the Prismatoid. If we understand what is Prismatoid, we can apply this one. Okay? Actually, no, the sphere, the cone, the cylinder, the pyramid, the the prisms, they are the basic type of prismatoids. Okay? They are all actually prismatoids. Let's have this one. We have this object that we are going to solve for the volume. And this is our, let us find a reference plane for our prismatoid. Okay? We choose this lower bottom of the sphere, this imaginary portion here of the sphere, the lowest part of our circle, as our reference datum. Okay, this is our datum. This is where the dimensions came from for this date for our calculations. Now let's go to our calculator, mode 33. Okay, mode 33. Actually, in our calculator, no, it's not mode 33 for my calculator, which is Canon. Let's see. We have this one. Oh, what is that in our display? Mode AC. I am in quartics equation. Mode 1. Okay. In this calculator, actually, for the older calculator, you can do mode 33. But what we are going to do here in the older calculator is this one. We are going to input, actually, the areas of the defined areas from our volume. So with reference from this datum plane, so we have this from this point, the distance of this point from this datum is actually 0. The midsection in here, okay, the distance from the datum is actually the radius 20, and at the top that is equal to 40. Okay, and we are going to enter the area here. The area here is 0 because that is the bottom edge of the, or that is not that edge, the bottom point of our sphere. And the area at the midsection is the great circle of the sphere, that is pi r squared. That is the r is 20. And the area at the topmost part of the sphere is also 0. Okay? That is our modeling in the calculator. Okay? Mode 33, volume by Prismatoid. Then we are going to find the value of A, B, and C. Okay? the value of A, B, and C, definition of the equation of this volume. Now, go to A is equal to 0. You can solve that. I will show to you how to retrieve this A, B, and C. Okay, you can store this B in the calculator, in the memory address. C is stored in the memory address. Okay, thus the A, you don't need to store that in the memory address because the value is 0. And before we are going to proceed with with the formula, how to use this in our calculator, I am going to do this in our Casio FX9 EX. That is Casio FX991EX class Wiz. Okay? The Casio class Wiz. You have this one. It's model.object. Menu is not number 6. Okay? And I will going to use number 3. I am going to discuss to you class why I use number 3 in here. Number 3. Take note that number 3, let us repeat that one, is quadratic regression in the statistics mode. Quadratic regression. So number 3, we have 0. Let's repeat that process. 0, 20, that is distances from the reference datum of the areas. The above is, the bottom is 0, the great circle, shift pi, the radius is 20 squared, that is the area of the great circle. Then 0 at the topmost of the point, the topmost point of our sphere. Okay? AC. And for our calculation, this is our formula. Okay? The integral of alpha A plus alpha B, alpha X plus alpha C, alpha X squared, dx limits from x1 to x2. That is the volume of the Presmatoid. General Presmatoid. Okay? That is the general Presmatoid. What is that A, B, and C? How to get that A, B, and C? Just go to option and you can find that from the regression number 3. Boom! We have this A 0. B is 125.6637061. C negative. What we are going to do here is to input these values, is to assign these values into memory addresses. Okay, let us assign B to memory address B. Let us assign C to memory address C. Okay, so we are going to retrieve this one by one. AC, option, downward arrow, regression number 4. So I am going to go outside this mode to do the integration calculation. Number 4, regression. Then we have this A, number 1. That is the value actually. 0. Do not write that into memory address. Doesn't matter. Then option again. Downward arrow, regression. Number 2. Okay, we have this value. 125 in terms of pi. There's no value in terms of pi. 125.663. Okay, store to A, store to B. Okay, it's already in the memory address B. Again, we have this option, downward arrow, regression, number 4 again. C, that is number 3. Then store, this is the value of number 3. That is negative 3.14. I think negative pi. You can see that. 3.14159. That's negative pi. Then store to C. All right. Our value of C is already at the memory address C. We can go out from the stat mode. Let us go to mode 1, the normal calculations. Okay. Then integrate alpha A. Let's not write that, alpha A. Alpha B. The value is at the memory address. Alpha X, this is the variable of integration. Alpha X plus alpha C. Alpha X squared. Okay? Limits. Of course, we are going to use limits from x1. Is from x1, 12. from the reference datum. Our dimensions are from reference datum. This is our reference. From x1, that is equal to 12, the distance, to x2. Okay, that is totally, what is that? 20 plus 14. Okay, 20 plus 14, that is 34. The 12 is 20 minus 8, that's 12. Okay, that will serve as our limits. We have this from 12 to 34. And let's wait for it. Wait for it. Very fast. That is the answer. 24236.34 cubic cm, baby. What happened here? Why the solution is this one? I did not understand the type of solution. Actually, no, we use the definition of the general Prismatoid, because the general Prismatoid is defined as a volume that any area from a reference datum, any cut area or any cut section parallel to a reference datum, a parallel plane, a reference plane, can be expressed in terms of its distance from the reference datum in a polynomial not higher than third degree. You get that? I hope I was able to express it correctly. Okay, let me illustrate that to you. Yeah, this, I turn it into pen. Pen. Let us say we have this reference. This is our reference plane. Okay, this is our datum. Then distance from that datum, we have this area. Okay, or I will create another figure. I think I will create another figure. We have this volume. Okay, and we take this plane as our reference plane. This is our reference plane. Okay, so if we can express any area parallel to this plane, any area cut in this volume, let us say this area, if we can express this area in terms of the distance, let's call the distance x from the reference datum. Okay, if the ax is not higher than third degree in terms of x, a polynomial in x, a function of x, not higher than third degree, then this volume is a Presmatoid. If it is higher than third degree, or if it is not a polynomial in x or a polynomial function of this distance, then it is not a Presmatoid. You cannot apply the solution. Now, how about the sphere? The sphere actually is a type of Presmatoid where you can express the area into second degree equation. Okay? The cone, the pyramid, you can express that in terms of linear equation. The area above in any reference datum. For the cylinder, you can express that as constant. The area are constant, so there is no variable here. X, B is 0 and C is 0 for the cylinder and for the prisms. Okay? So we are talking about the spherical frustum. So we have this second degree equation. That's why this is our equation. Okay? If you know this equation, you have the area. Create a thickness to that area. Okay? To turn this into integration, create a differential strip. You have the differential volume. So this is now our dx. See that? That is our dx. That's why what is this volume? Differential volume. The differential volume is area in terms of x times dx. What is the area? The area is according to this equation fx, and for the case of sphere, this is our fx. All right? That's why we have this formula. Fortunately, this is a second degree equation. We can model that into the this is not into the quadratic regression in our stat mode of our calculator. All right, that is our answer, baby. For this problem so far, this approach is not attractive, but there are instances that this is the right solution for the problem at hand. Okay, another solution for this problem, baby. Now this one. The Presmoidal formula. The previous solution, that is for the general Prismatoid. This one is the Presmoidal formula, where you need to find the area of the midsection. So this is the volume if you memorize the formula for the volume. Okay, you memorize the formula, L over 6, area 1 plus 4 times the area of the midsection plus area 2. Okay, what is the L? Our L actually here is the vertical distance between the bases, between the area 1 and the area 2. So, meaning the perpendicular distance between these two bases, that is equal to 22, 8 and 14. All right? 22 cm. Okay? The area of the midsection, we are talking about 11 from both ends. So, we are talking about that section. The distance from this end is 11. The distance from the upper end is 11. So, we already know the dimensions of this lower base and the upper base. We need to find the dimensions of this midsection. What is the radius of this midsection? Let us call that Rm. We know that this is 8, right? So, what remains here is 3, because a total of 11. So, by Pythagorean theorem, we can find this Rm. I will not write it here. Okay? You can do that yourself. That is 20 squared minus 9 squared. Square root of that is the value of Rm. I think you don't need the value of Rm, but you need the value of Rm raised to 2. Okay? So, if we are going to call the radius here as capital R, the radius here as small letter r, okay? Therefore, our formula will become L over 6 pi r squared, that is the lower base, plus 4 pi Rm squared, that is for the midsection, and the upper is pi r squared, the upper base. All right, substitute. We have this L is 22. We have this a squared. We solve this in the first solution, the traditional solution, and we have this one. You can do that by Pythagorean theorem. That is the r squared, and we have this also from the first solution in the traditional solution. We already solved this one. Calculate. Chicken joy, baby. That is the answer. Okay. Let's go back to our larger display without the calculator. Okay. Check. All right. That is our answer. The same answer to our two previous solutions. Another approach for this problem is by, what is this? By integration. Okay? This is so far the best solution for this problem. That is in my perspective. Maybe in your end, it's not the best approach. But for me, this is the fastest way to solve this problem. Okay? You can adapt any type of solution as long that you have the solution. That's the most important part. You have the solution. You will not get stuck in this problem. Okay? How to do that? We are going to superimpose the xy plane at the origin of at the center of our sphere. So we are going to make this point the origin of our xy plane. And therefore, we can define the circle. Okay? That is the required prerequisite for using integration. You need to create an equation, meaning analytic geometry. Okay? What is the equation of the circle? Can you recall for your analytic geometry? For the equation of the circle center at the origin given radius. The radius of this is 20. So therefore, the equation of this is x squared plus y squared is equal to 20 squared. That is the standard equation of the circle. Center at the origin, radius 20. All right? Now, how to solve this volume? By integration. Let us create a differential volume or the differential element. This is our differential element. Okay, and let us forget the whole volume. Let us concentrate our energy to this differential element only. That's the beauty of integration. The complicated object will reduce into a very simpler geometry. This will become a very thin cylinder of radius. Let us call that x. That is the radius of our cylinder. Okay? And the thickness or the height of our cylinder is dy. Now, let us define this volume only, not the whole volume. This strip only, or the differential element, we call this the differential element. What is the volume of this differential element? Of course, that is a differential volume. This is equal to what? Cylinder. Very thin cylinder of radius x, height dy. The base is circle. Okay, so the area of the circle, that is area of the base, pi x squared. Okay, that is the area of the base times the height, dy. That is the differential volume of this element. Okay, how to find the total volume? Let us sum up all the differential element from this point up to that point. Okay, so this differential element will sweep this volume upwards, so that you can get the total volume. So, after integration, you can get the total volume. So, we're going to sum up this one. That is the equivalent summation in differential values. Okay, differential elements. We are summing up differential elements. Pi x squared dy. And we have limits. We need limits. Because our differential element is dy, we are going to pick limits from the y from the ordinates. Okay, so from y1 to y2. If our differential elements are dx, we are going to pick up limits from the abscissas. In this case, because we are dy, from the ordinates. All right, so we have this one. The volume is pi. We have this dy. So we need to express our equation so that we can put it in our calculator, to the calculator. We are going to express our equation in terms of y alone. Now, we have this x squared. So, we are going to replace this x squared by y, in terms of y. How to do that? How to express this x in terms of y? We are going to use the equation because this x actually happens to be in this circle. The length of this x happens to end in the circle. It will terminate at this point, and this point is part of this circle. And the equation of the circle is this one, which means that this x squared is equal to this x squared, which is equal to 20 squared in terms of y minus y squared. What is that? Y squared. This is y squared. Let me replace that. Let us replace that. Okay? Your screen is wrong. Hard. Let us replace that. That is actually x is y squared. Okay, save. I hope get updated. Where are you? Oh, I lost my presentation. You are already here. Okay, then sum up. We already have this correct equation, 20 squared minus y squared dy. Okay, in terms of y. Then sum up. Limits. What is the value of y at the bottom? Take note that we are at the xy plane. So the value of y at the bottom is 8. It's not 8. Negative 8. We are at the bottom below the origin. Negative 8, the value of y. To the top, the value of y is 14. Integrate using your calculator. Chicken joy, baby. Let's do that here. Okay. Casio calculator. Let's load that. Let me check. Okay. Mode 1. The integral of 20 It's not responsive. 20 minus, of course, we will use alpha x, not alpha y, because we have this dx. Alpha x squared dx. Okay? Limits from negative 8 to positive 14. Okay, let us put pi in the... Hey, shift pi. This is our answer. What happened from negative 8 to 20 squared, not 20. 20 squared. This is our answer. 23144 over 3 of pi, or that is 2436.34, baby. Okay? That is our answer. For me, personally, this is my preferred solution. How about you? Okay? Do you have another type of approach for this problem? Share it to us. Okay? Hello, guys! Welcome back to my channel. Bye-bye! Stop